we are so back. So, school has been way too crazy, way too much work, literally. So, half of my summer's gone as well for some reason, probably because I couldn't be bothered doing anything. But here I am, making the 10th video on this channel, so I hope you enjoy it. Today we are integrating the natural log squared of x to the 4th plus 1 divided by x cubed dx from 0 to infinity. And to do this integral, we are going to do some contour integration, which I don't think we've done on this channel before, so that's going to be a first. So yeah, let's get started. So what I'm going to do is I'm going to name this integral I, because we will need it. Well, not really, to be honest, but it helps. And we are going to transform this into a complex function. We'll transform the integrand into a complex function, and we'll just do that simply by using the principal branch of the complex log. So I'm going to denote that by capital L log, because I think that's just notation, but that's our function that we're going to integrate over, and we can actually split the log up into its real and imaginary parts. So we'll just do that. So it's going to be the absolute value, that's going to be its real part, and the imaginary part's going to be the argument of whatever's inside it. So that's going to be our function. So to actually carry out our contour integration, obviously we're going to have to pick a contour, but we can't do that without finding where the branch cuts are. As you can see, I've drawn two complex planes here. Maybe I should have labeled them. But anyways, this plane over here is the plane that we're going to integrate over. And to find the branch cuts, we're going to have to look at the image that this plane maps onto. So let's say we map onto the other plane by log squared z to the 4th plus 1. And because we're using the principal branch of the complex log, we know there must be a branch cut along the negative real axis. So the argument goes from negative pi to pi. And reversing the action, because this starts at 0, we're going to have 4 branch cuts, starting at the root of the polynomial z to the 4th plus 1. So here are the 4 roots, and they're going to have the form e to the I pi over 4, and so on. And our 4 branch cuts, if we reverse this map over here, they are actually going to be radially outwards, like 45 degrees, like that. So that's going to be quite helpful. We're going to have our 4 branch cuts, and let's see if we have any poles. So we see a z cubed in the denominator, so that must mean a pole at 0. But that pole's actually removable. So I believe if you set f of 0 equal to 1, the neighborhood around 0 is all like holomorphic and nice. So we don't really have to worry about that. It's removable. Who cares? So I guess we are ready to pick our contour now. So looking back to our integral, we are integrating from 0 to infinity. So obviously we're going to have to include this path. And as I said, 0 is removable, so not going to avoid that one. And we're going to go up to r. And I'm going to let r tend to infinity at the end. So that's the first part of our curve. We're going to go anti-clockwise, and we're going to go up like a circle. And we can't hit the branch cut, so we're going to take a detour, go around the branch point, go back up, and around back like a circle, and hit the positive imaginary axis, and come straight back down. The reason I didn't go, let's do red. The reason I didn't go all the way around here and like go down here and take back this path is because if you look at our function, it's an odd function. So if we include the negative real axis, it's just going to be 0, and we're going to have no help at all. So that is going to be our contour. And now let's label some things. So we've labeled 0 to r. Let's call this gamma 1. Let's call this gamma 2. I'll call this psi 1. I'll call this psi 2. And that little gamma. And for the last curve, well, that's going to be IR. I'm not going to label anything. That's just that. So I'll add some arrows just to make this look nicer. It might be the thumbnail. Who knows? I might make something special for the thumbnail. Anyways, I guess we're ready to start integrating. So, as we can see, no poles within the contour. Not even any poles anywhere, to be honest. So, Cauchy's residue theorem plays in. We're going to integrate over the entire curve, and that's going to be equal to 0. But that's going to be also equal to our integral from 0 to r plus, let's write the IR to 0 first. Yeah, and then we'll sum over the big gammas, the little gamma, and the two sides. Why is this wonky? Don't know why it's going wonky, but anyways, that's fine. And I'm not going to worry too much about the details. You can try to prove them on your own. Gamma 1, why are the two gamma 1s over here? Right, so the two gammas, as r goes to infinity, by the estimation number, they're just going to go to 0. So you can try to prove that. I mean, z cubed grows faster than log anyway, so shouldn't be too hard. And gamma shrinks, well, little gamma shrinks as we let that radius go to 0, so that's going to go to 0 as well. So we honestly only have 4 integrals to worry about. And let's worry about IR to 0 first. Well, no, 0 to r first, because when we let r tend to infinity, that's just going to be equal to I. So that first integral is going to be equal to I. Now let's figure out what IR to 0 should be. So let's write that down. Integral IR to 0. And because we're going down the positive imaginary axis, we're going to parameterize this. So let's parameterize this as z equals it. And I don't like this that flipped bound, so that's going to go from 0 to r at the cost of a minus sign. And every z in the function is going to be replaced with it. So it to the fourth, actually, plus 1 divided by it cubed. We have a dz, but we'll need to replace it with dt. So dz is idt, of course, and idt. There we go. And so let's do some tidying. Let's keep that there for now. Log squared of, well, it to the fourth is just t to the fourth. So that's going to stay as that. Negative I is going to pop out. T cubed, I dt. I divided by I is just nothing. And 2 negative signs. So we're left with this. And what's this exactly? That's exactly equal to I when r tends to infinity. So that's also equal to I. And yeah, we only have psi 1 and psi 2 to worry about. And they are the most annoying things ever, I can tell you. But let's do it. So let's take a look at what psi 1 and psi 2 are actually doing. They are approaching the pi over 4 branch cut. What that means is they are approaching this path. And I'm going to call this path lambda. That's going in the outwards direction. And when they actually hit the branch cut, psi 1 is going to go in the opposite direction of lambda, and psi 2 is going to be going in the same direction as lambda. So if I were to write this out, psi 1 plus psi 2 is going to be equal to negative lambda for psi 1 and positive lambda for psi 2. Now, these might look like they can cancel out, but they can't, because, well, psi 1 and psi 2 do have the same modulus, but they don't have the same argument, so we'll have to be super careful here. But anyhow, let's write this out. So the negative one is going to be the integral of negative of this absolute monstrosity, and I'm just going to write this out. So let's cut to when I'm done writing this out. There we go. And we'll do the same for the positive one. Right, so I've done that, and I'm going to expand both brackets. So let's do that. So it's absolutely huge now, and I've had to be very careful with like these eyes dotted around, just made very confusing. But anyways, things start to nicely combine and cancel out, etc. So these two cancel out. As I said, the modulus, they're the same on both sides, so that's going to be fine. But when it comes to the arguments, we can't just cancel, for example, this term and that term out, because the arguments are different. So this argument comes from psi 1. Let's check out the arguments for both sides. So psi 1, when it's mapped onto the other plane, psi 1 is going to go up there, and psi 2 is going to go down there. And as we can see, let's do f of psi 1. Yeah, that makes sense. And f of psi 2. So psi 1 is going to have an argument of pi. Psi 2 is going to have an argument of negative pi. So let's just plug that in. Argument of psi 1 is pi. Argument of psi 1 is pi. So that's going to be pi squared. Argument of psi 2 is going to be negative pi. And argument of psi 2 is negative pi, yes. So negative pi squared. And we see the pi squared and this pi squared, because negative times negative is positive, they cancel out, so these two cancel out. But the middle two bits don't, and let's just write this out better. So that's going to be the integral of, so that's negative of this bit times pi, and negative of this bit times pi. That's the same thing. So that's going to be minus 4i, I think. Yes, yeah, so it's going to be minus 4 pi I times log z to the 4th plus 1 over z cubed dz. And we're ready to continue integrating. So let's pull the minus 4 pi I out first. And we also have to parameterize this. So let's take a look at this. We are going from e to the I pi over 4 to infinity, basically. So in that direction, actually. So if we set a parameter, let's say t times e to the I pi over 4, and range it from 1 to infinity, that's going to get us that lambda line. So if we go from 1 to infinity and set, let's write it here, z equals t to the, not t to the, t times e to the I pi over 4, and dz will be, well, e to the I pi over 4 dt. What that means is we replace everything, every z, with t times e to the I pi over 4 to the 4 plus 1, and then t times e to the I pi over 4 cubed times e to the I pi over 4 dt. Now, let's take a look at this middle bit. So t times e to the I pi over 4 to the 4th power. That 4th power is going to rotate it to minus 1. So that's going to be minus t, or minus t to the 4th. And that's going to become 1 minus t to the 4th. And the bottom, let's see, well, t cubed, there's going to be a t cubed. It's going to cancel out one copy of that, becoming a squared. Hope I've done that right. Which means that's going to be I. So that's going to be an I. And nicely cancelling out with the I out front. So that's going to be it. And let's fix the log a bit. So t ranges from 1 to infinity. T is bigger than 1, so the thing inside must be always negative. So let's flip that because we have an absolute value. So that's going to be log t to the 4th minus 1. And let's shrink that fraction thing a bit. And because we're back to real numbers, that can just be a natural log. So yeah, we have another bonus integral, I guess, and let's integrate this one as well. So what I'm going to do next is I'm actually going to multiply by t on the top and bottom at the same time. And what that's going to do it's going to generate a t to the fourth at the bottom and a t up top. That means I can do a u sub of u equals t squared, because when I do du, it's going to give us 2t dt, and I can absorb the t at the top, and I can also steal a factor of 2 out front. So that's going to be natural log of u squared minus 1 divided by u squared du, and the bounds don't change in this case. And seeing this u squared minus 1, I did a trig sub, so u equals secant theta, because that's the trig sub for u squared minus 1, and minus 2 pi. The bounds actually change here, so they change from 0 to pi over 2. You can verify that. And it's quite nice in the natural log, because secant squared minus 1 is just tangent squared theta. So that's quite nice, and secant squared theta at the bottom. And figure out du is just tangent theta, secant theta, d theta. So let's just write that in. And one of the secants is going to cancel out, so that's quite nice. And also, tangent theta divided by secant theta is sine theta. So sine theta is out front. Well, not out front, but like here. And times natural log tangent squared theta. And yeah, that's kind of another form of the integral. And seeing the sine theta out front, I was determined to get a cosine theta within the natural log, so we can do some u subs. So seeing the tangent squared theta, naturally I split this up into sine squared theta divided by cosine squared theta, because I know if we divide within the natural log, we can split this up. And so I also replaced sine squared with 1 minus cosine squared theta, and then factorize a 1 minus cosine squared to 1 plus cosine and a 1 minus cosine. And that makes everything so much easier to integrate. And that also means we can split this natural log into 3 integrals. So I'm going to do that right now. There we go. So I've expanded it into 3 integrals. We have this factor of 2 because of the squared there, but everything's just because of log rules. So we're ready to do some u subs finally, and I'll just do that. Yeah. Cut. There we go. That also changed the bounds a bit. And to make this easier, I'm going to do, for the first integral, I'm going to do t equals 1 plus u, and for the second one, I'm going to do t equals 1 minus u, just to make it simpler. There we go. And as you can see, the last integral takes away 1 extra copy of the middle integral, so I'm just going to combine those two. And we're ready to actually integrate this, so let's plug the integrations in. Natural log of t integrates to t natural log of t minus t. If you're wondering, that was from integration by parts, but that's quite common, to be honest. So now we're ready to plug it in. So we're going to have 2 natural log 2 minus 2 minus 1 times the natural log of 1. Well, that's just 0. And then plus 1 minus 1 times natural log of 1, which is 0, minus 1, and minus 0 times, well, 0. So that's just 0. There's some weird limit stuff going on. I'm just going to, ignore that. I'm just going to say it works. You can check it works. Don't know, do some L'Hopital's or something. Anyways, that gives us 2 pi times 2 natural log of 2 minus 2 plus 1 plus 1. So the final constants cancel out. And that leaves us with minus 4 pi times natural log 2. And remember, this was equal to psi 1 plus psi 2. And so, going back here, 0 equals 2i, because we have 2i, yeah, and then minus 4 pi natural log of 2. That means 2i is equal to 4 pi of natural log of 2, or 4 pi times natural log of 2, and I equals 2 pi times natural log of 2. Thank you very much. That is the result. And yeah, that was crazy. That was quite cool. We had one bonus integral. Well, many forms of one bonus integral. Feel free to take a look at any of these forms. But yeah, that was nice. This is equal to 2 pi times ln 2. Bye!